Hello, welcome back, wherever you are tonight, and I find myself wondering, genuinely, at this hour, what particular shape of stillness has settled around you, what quality of light or dark fills the room, whether there's some small, familiar sound nearby that tells you exactly where you are without needing to think about it. I'm glad you're here. This is a good hour to have arrived at. Whatever the day held, it's behind you now. Go ahead and settle in properly. Not the tentative kind, still half listening for something else. The complete kind. Let your weight become entirely real against whatever is holding you up. Let your shoulders finally set down whatever they've been carrying. Let your breathing slow into its own rhythm, unmanaged, unforced. You don't need to hold on to anything tonight. What stays with you will stay because it found something in you already waiting for it. The rest will simply pass through, gently, and that's exactly as it should be. This isn't a lesson to be studied. It's a long, slow unfolding of something true, offered at whatever pace lets your eyes close on their own. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down until they fit the shape of a quiet evening. If this feels like somewhere you'd like to return to, a gentle like or subscribe helps other people find their way here too, on their own restless nights. But that's for later, for the more awake hours. Right now, there's only this. Tonight, we're going to talk about a boundary. Not a wall, exactly, though it does, in its own strange way, function a little like one. A vast, invisible, constantly shifting membrane surrounding our entire solar system that most people have never heard of, and that very few people properly understand. Even though, in a very real sense, every single living thing on Earth owes its continued existence, at least in part, to its protection. It's called the heliosphere. And for most of human history, we simply didn't know it was there at all. We knew, of course, about the sun. We knew about the planets, the asteroids, the comets that occasionally swept through our skies. But the idea that our entire solar system, the sun, all 8 planets, all of their moons, the asteroid belt, even the distant icy reaches of the Kuiper belt, sits inside a kind of vast, invisible bubble carved out of interstellar space by the constant outward pressure of the sun's own breath, was something we only began to properly understand within the last several decades. And it was only within the last dozen years or so, thanks to 2 extraordinarily patient, extraordinarily long-lived spacecraft, that we finally actually crossed that boundary and found out directly, firsthand, what lies immediately beyond it. And what we found there, what the Voyager spacecraft have been quietly, faithfully reporting back to Earth in fragments across more than a decade of continuous interstellar travel, is stranger, and in certain specific ways more violent than almost anyone expected. Tonight, we're going to talk honestly about that boundary and about what actually lies beyond it. I want to be careful at the outset to promise you something. This is not going to be a story designed to frighten you. There is a great deal of overheated, exaggerated language that circulates online about this particular topic, treating every genuine scientific surprise as though it were evidence of imminent danger. That's not what we do here. We're going to look, instead, carefully, honestly, at what the actual data shows, some of which is genuinely more intense, more violent, more surprising than earlier models predicted, and all of which, properly understood, reveals something quietly remarkable about the specific, delicate conditions that have allowed a small, blue planet, orbiting an ordinary star, to remain safely habitable for billions of years. Close your eyes when you want to. Let's begin. Let's start with something you already, quietly, intuitively know, even if you've never had a name for it. The sun is not simply a source of light and warmth, sitting passively at the center of our solar system. It is also continuously, actively, breathing outward, releasing a constant, steady stream of charged particles electrons and protons mostly, flowing outward from its surface in every direction, at speeds typically ranging from around 250 to 500 kilometers per second. This continuous outward flow has a name: the solar wind. It's not wind in the sense you're familiar with here on Earth, not moving air, since space itself contains essentially no air to move. It's a thin, but genuinely physical, stream of charged particles, constantly pouring outward from the sun, filling the entire volume of our solar system, carrying with it the sun's own magnetic field, stretched and dragged outward into a vast, spiraling structure that extends, eventually, far beyond the orbits of even the most distant planets. As this solar wind travels outward, its pressure, the sheer, cumulative push of countless charged particles moving fast in a consistent direction, gradually weakens the farther it travels from its source. The same way, in a much more familiar sense, the warmth of a fire gradually fades as you move further away from it. Eventually, at some considerable distance from the sun, the solar wind's outward pressure weakens enough that it can no longer overcome the competing inward pressure of a completely different kind of environment. The interstellar medium, that vast, extraordinarily thin but genuinely present material, mostly hydrogen and helium gas, along with scattered dust and high-energy particles, that fills the space between individual star systems throughout our entire galaxy. Where these two pressures meet, where the sun's own outward breath finally, gradually, loses its battle against the wider pressure of interstellar space, a boundary forms. Astronomers call this boundary the heliopause, and the entire vast, roughly bubble-shaped region enclosed within it, everything from the sun itself outward, through all 8 planets, through the asteroid belt, through the Kuiper belt, all the way out to this final, outermost boundary, is called the heliosphere. This is, quite genuinely, one of the most important structures in our entire cosmic neighborhood, and until remarkably recently, we understood almost nothing about it directly, because no instrument built by human hands had ever actually traveled far enough to reach it. That changed, first, on August 25th, 2012, when NASA's Voyager 1 spacecraft launched in 1977, and, by that point, already 35 years into what was originally intended to be a much shorter mission, became the first human-made object in history to cross the heliopause and enter genuine interstellar space. This was, by any reasonable measure, one of the great achievements in the entire history of space exploration. A spacecraft launched during the same decade that gave us disco music and the earliest home video game consoles, traveling far enough, faithfully enough, patiently enough, to finally leave the protective bubble of our entire solar system behind and begin sending back, for the very first time in human history, direct, first-hand measurements of what actually exists in the space between the stars. But here is where our story tonight properly begins, because Voyager 1's historic crossing, remarkable as it was, came with a genuine complication. Due to a specific instrument malfunction, the spacecraft's plasma science detector, the instrument specifically designed to measure the density and behavior of charged particles around it, had stopped functioning years earlier, in 1980, shortly after its Saturn flyby. Voyager 1 was unable to properly, directly measure many of the specific characteristics of the boundary it had just crossed. Scientists on Earth had to infer, indirectly, through other available instruments, that the crossing had genuinely occurred, rather than measuring it as cleanly and directly as they had originally hoped. This is where Voyager 1's twin spacecraft, Voyager 2, becomes genuinely important to tonight's story. Launched slightly earlier than its sibling, in August 1977, but following a longer, more circuitous route through the outer solar system, one that included historic flybys of Uranus and Neptune, which we've discussed together in earlier conversations here at Late Space. Voyager 2 finally crossed its own heliopause boundary 6 years later, in November 2018. And critically, unlike its twin, Voyager 2's plasma science instrument was still fully functional. For the first time in human history, scientists finally had a spacecraft crossing this critical boundary, capable of directly, cleanly measuring exactly what was happening there. Wherever you are, I hope you're comfortable. Let's take a moment here before we go further, because what Voyager 2 actually found when it crossed that boundary turned out to be genuinely, legitimately more intense than the models had predicted. And I want to walk through this carefully, honestly, with all the appropriate scientific nuance, rather than either dismissing it or exaggerating it. According to research published following Voyager 2's crossing, and led in significant part by Edward Stone, an astronomer who had worked on the Voyager program continuously since its original 1977 launch, the temperatures recorded within the heliopause boundary itself reached as high as 89,000 degrees Fahrenheit, roughly 31,000 degrees Celsius. This figure was, notably, roughly double what previous astronomical models had predicted for this specific region. I want to be careful here, because a number like 89,000 degrees, spoken aloud, sounds almost apocalyptic. The kind of figure that seems, at first hearing, like it should represent some kind of genuine physical danger. And I think it's worth pausing properly to understand what this temperature measurement actually means in physical terms, because the reality is considerably stranger and considerably less alarming than the number alone might suggest. The heliopause is an extraordinarily thin, extraordinarily sparse region of space, the hot plasma detected there, while genuinely, technically at an extraordinarily high temperature in the specific physics sense of that term, meaning, specifically, that the individual charged particles within it are moving at extraordinarily high velocities, exists at such an incredibly low density, so few particles occupying such a vast volume of space that this heat carries essentially none of the practical, everyday danger we associate with high temperatures here on Earth. If you could somehow stand within this 89,000 degree plasma, you would not burn or melt or experience anything resembling the effects of standing near an actual fire of that temperature, because there simply aren't enough particles present in any given volume of space to transfer that thermal energy to you in any meaningful way. The heat is real in the specific physics sense, but it is a heat almost entirely without substance, present in the extreme velocity of a very small number of particles, rather than in any kind of dense, transferable thermal mass. What this unexpectedly high temperature genuinely reveals, scientifically, is something considerably more interesting than danger. It reveals that the collision between the outward-pushing solar wind and the inward-pressing interstellar medium, happening continuously at this boundary, is considerably more energetic, more dynamically violent. In the specific physics sense of particles colliding, exchanging energy, and reaching higher velocities than anticipated, than earlier theoretical models had properly accounted for. Let me tell you about the second major surprise Voyager 2 revealed, because I think it's genuinely the more important and certainly the more consequential of the two. According to the same body of research, this unexpectedly hot, dense plasma boundary functions as something considerably more significant than simple decoration at the edge of our solar system. It appears to function as a genuine, physical shield, actively blocking a substantial portion of the high-energy cosmic radiation that otherwise fills interstellar space. Specifically, the research suggests that this heliopause boundary, this hot, thick wall of colliding plasma, stops approximately 70% of incoming cosmic radiation from ever reaching the inner solar system at all. I want to sit with this figure properly, because I think it's genuinely one of the more important and quietly reassuring pieces of information in tonight's entire conversation. Cosmic rays, extraordinarily high-energy particles, accelerated to tremendous velocities by distant supernova explosions and other violent astrophysical events scattered throughout the galaxy, are, in sufficient quantities, genuinely harmful to biological life. They can damage DNA, disrupt delicate biological processes, and, in significant enough doses, pose genuine radiation hazards to any living organism exposed to them without adequate protection. The fact that our heliosphere, this vast, invisible bubble carved out by our own sun's constant outward breath, appears to be filtering out roughly 70% of this potentially harmful cosmic radiation before it ever reaches the inner solar system, is a genuinely significant, genuinely important piece of planetary protection. It means that Earth and everything living on it has spent billions of years developing and evolving within an environment that is measurably, meaningfully safer than the wider interstellar space surrounding it, specifically because of this vast, largely invisible, continuously active solar shield. But, and this is where tonight's story takes its next, more genuinely nuanced turn, the same research that revealed this protective effect also revealed something considerably less reassuring. This shield is not perfectly uniform. It is not, as researchers had perhaps hoped or assumed, a perfectly smooth, perfectly sealed, uniformly protective bubble, evenly blocking cosmic radiation across its entire surface. Instead, the data suggests that the heliopore's boundary contains what researchers have described as porous regions, specific, localized areas where the boundary's protective effect appears to be weaker, allowing measurably more interstellar radiation to leak inward than the surrounding regions of the boundary permit. This finding matters, genuinely, for how scientists understand the overall structure and behavior of our solar system's protective bubble. Rather than a perfectly sealed, uniformly effective shield, the heliopause appears to be something more like an imperfect, unevenly permeable membrane, highly effective, overall, at blocking the majority of incoming cosmic radiation, but with specific, identifiable weak points where that protection is measurably reduced. I want to be careful, again, about the appropriate scale of concern here. This does not mean that dangerous radiation is currently actively pouring into the inner solar system through some kind of significant breach. The overall protective effect, that 70% reduction in cosmic radiation, remains genuinely, measurably significant and effective. What this finding reveals, more precisely, is that our previous, simpler models of the heliosphere as a perfectly smooth, uniformly protective bubble were, in this specific respect, somewhat too simple. That the actual, physical reality of this boundary is more complex, more textured, more genuinely three-dimensional in its structure than earlier theoretical models had properly captured. Wherever you are, I hope you're comfortable. Let's breathe here for a moment before we continue further outward into the genuinely strange territory that lies beyond this boundary entirely. Because once Voyager 1 and Voyager 2 had each, in turn, crossed the heliopause and entered true interstellar space, they began sending back something genuinely unprecedented in the history of our species: direct, first-hand measurements of the actual environment existing between star systems. Data that, until that moment, had existed only in theoretical models and indirect inference, and that had never, ever been directly, physically measured by any instrument human beings had built. And what these spacecraft found, in the years since crossing that boundary, has continued to genuinely surprise the scientists studying the incoming data. Not in a way that suggests danger, exactly, but in a way that reveals, repeatedly, patiently, across more than a decade of continued observation, that our previous theoretical understanding of this region was considerably less complete than we had assumed. Let me walk you through some of these specific findings, carefully, because I think each one reveals something genuinely worth understanding properly. The first genuine surprise involves the interstellar magnetic field itself, the large-scale magnetic field that permeates the space between star systems throughout our galaxy, distinct from, but interacting with, our own sun's magnetic field. Prior to Voyager's direct measurements, scientists had generally modeled and predicted that this interstellar magnetic field would be oriented at a different, distinct angle from our own sun's magnetic field, that crossing the heliopore's boundary would involve passing through a region where the magnetic field's direction shifted noticeably, marking, in a sense, the transition from our magnetic environments to a genuinely separate, differently oriented interstellar one. Instead, both Voyager spacecraft found that the interstellar magnetic field immediately beyond the heliopause appeared to be oriented in almost exactly the same direction as our own solar system's magnetic field. A finding that genuinely surprised researchers, and that remains, even now, an active area of ongoing scientific investigation and discussion. Merav Ofer, a heliophysicist at Boston University who has worked extensively with Voyager data, described this specific finding with genuine, evident scientific candor. The interstellar medium, as measured by the Voyager probes, is not quiet. It's agitated and influenced by the sun. It's so different than we expected, and we still don't really understand what's going on. I want to sit with that quote for a moment, because I think it reveals something genuinely important about the honest, ongoing texture of real scientific discovery. Considerably more honest, and considerably more interesting than the tidy, fully resolved narratives we sometimes expect from popular science coverage. A working, respected scientist, studying data collected by an instrument that has now been sending back information for well over a decade, openly acknowledging that a fundamental aspect of what that data shows remains, genuinely, not yet fully understood. The second significant finding involves the behavior of cosmic rays themselves, once you're actually within interstellar space, beyond the heliopause boundary. Prior to Voyager's direct measurements, the general theoretical expectation was that galactic cosmic rays, those same high-energy particles we discussed a few minutes ago, largely blocked by our heliosphere's protective shielding, would arrive at any given point in interstellar space relatively uniformly from essentially every direction with no particular directional preference. Instead, both spacecraft detected a genuine, measurable directional pattern, what scientists call anisotropy, in how these cosmic rays actually arrive. Specifically, researchers found a clear reduction in the intensity of certain higher energy cosmic ray particles arriving from directions perpendicular to the surrounding magnetic field, compared to particles arriving from directions more closely aligned with that field. We thought we'd see galactic cosmic rays coming from all directions, Ofer noted, discussing this specific finding, but they don't. This directional pattern reveals something genuinely important about the underlying physics of this region, that the magnetic field structure surrounding our solar system, even well beyond the heliopause boundary itself, continues to meaningfully influence and organize the behavior of cosmic radiation in ways that considerably more simplified, earlier models had not properly anticipated or accounted for. And there is a third finding, perhaps the most genuinely fascinating of the three, involving something researchers have described as an ongoing, active connection between our own sun's activity and conditions occurring well beyond the heliopause boundary, deep within what should, by earlier expectations, have been considered genuinely separate, undisturbed interstellar space. Voyager data has revealed that specific solar events, particularly coronal mass ejections, enormous eruptions of charged particles, and magnetic energy that periodically burst outward from the sun's own surface, continue to create measurable disturbances in the surrounding magnetic field, extending well beyond the heliopause, deep into what researchers had previously assumed would be relatively undisturbed, purely interstellar territory. This finding has genuinely forced scientists to reconsider some of their basic assumptions about exactly how far our sun's influence actually extends, and about exactly how cleanly, how definitively, the boundary between our solar environment and genuine interstellar space actually separates the two regions from one another. Voyager 1, as of its 10-year anniversary of crossing into interstellar space, had travelled a further 40 astronomical units beyond the heliopause boundary itself, and even at that considerable additional distance, continued to detect these solar-influenced disturbances rippling outward through the surrounding interstellar magnetic field. Wherever you are, I hope you're still comfortable. I want to address, directly and honestly, something that I know has circulated fairly widely in less careful corners of the internet regarding these Voyager findings, because I think addressing it properly, honestly, is actually important to tonight's conversation rather than something to simply avoid or ignore. You may have encountered, somewhere online, considerably more dramatic, considerably more alarming claims about these Voyager discoveries. Suggestions that the spacecraft detected some kind of enormous, dangerous interstellar plasma cloud moving directly toward our solar system, potentially threatening to weaken or collapse our protective heliosphere shield entirely, exposing Earth to dramatically increased levels of dangerous cosmic radiation. I want to be genuinely careful and honest with you about this, because I think it illustrates something important about how real scientific findings sometimes become distorted, exaggerated, and sensationalized as they travel through less careful corners of online media, and because distinguishing carefully between what the actual science shows and what more sensationalized coverage sometimes claims is exactly the kind of careful, honest work I want this particular evening's conversation to model for you. The genuine, peer-reviewed scientific findings we've discussed tonight. The higher than expected heliopause temperatures, the porous, imperfect nature of the boundaries radiation shielding, the unexpected alignment of interstellar and solar magnetic fields, the directional patterns in cosmic ray behavior, the continued influence of solar activity well beyond the heliopause, are all genuine, legitimate, carefully verified scientific results, published in respected, peer-reviewed journals, discussed openly and honestly by the working scientists who conducted this research. Claims of an approaching, dangerous interstellar plasma cloud, actively threatening to collapse our protective heliosphere and expose Earth to sudden, dramatically increased cosmic radiation, do not appear in this same body of legitimate, peer-reviewed scientific literature. This kind of claim appears to originate from considerably less careful, less scientifically rigorous sources. The kind of content that takes genuine, interesting scientific findings and, in the process of trying to generate more dramatic engagement, stretches and distorts them well beyond what the actual underlying evidence supports. I mention this not to lecture you, but because I think it's genuinely important, particularly at this hour, in this particular kind of quiet, careful conversation, to model the difference between legitimate scientific uncertainty, which is genuinely present, genuinely interesting, and genuinely worth exploring, exactly as we've been doing tonight, and manufactured, exaggerated alarm, which serves mainly to generate anxiety rather than genuine understanding. The real science is genuinely fascinating enough, properly understood, without needing to be exaggerated into something more dramatic than what the actual data shows. So let's return, now, to what the genuine, carefully verified science actually reveals, and let's spend some time properly understanding what it means at the appropriate, honest scale of significance, neither dismissively minimized nor artificially inflated into something more alarming than the evidence supports. The heliosphere, our solar system's vast, invisible protective bubble, is genuinely more complex, more dynamically active, and in certain specific ways more surprising than earlier, simpler theoretical models had predicted. It contains regions of unexpectedly intense, energetic plasma activity at its boundary. It provides genuine, significant protection against cosmic radiation, blocking roughly 70% of incoming cosmic rays. But that protection is imperfect, containing specific, identifiable weak points where radiation more readily leaks through. The interstellar space immediately beyond this boundary is not the calm, uniform, purely external environment earlier models had assumed, but instead remains measurably, meaningfully influenced by our own sun's ongoing activity, extending its influence considerably further outward than previously understood. None of this represents a genuine, immediate threat to life on Earth. What it represents, instead, is something I find considerably more interesting and genuinely more worth our careful attention tonight. A picture of our solar system's relationship with the wider galaxy that is considerably more dynamic, more actively contested, more genuinely fought for than our earlier, simpler mental models had suggested. I want to spend some time now with a specific, particular idea that Merav Ofer raised in discussing these findings, because I think it deserves careful, unhurried attention here at this hour, in this particular quiet. Ofer has suggested, based on her extensive work with this Voyager data, that the heliosphere has likely played a genuinely crucial, protective role in shielding life on Earth from hazardous cosmic rays and dust across the entire multi-billion-year span of our planet's biological history. And she has further suggested something genuinely worth sitting with tonight, that our solar system's specific position within the wider interstellar medium, the particular region of the galaxy we happen to be travelling through, the particular density and character of the interstellar material our heliosphere happens to be pushing against, may have been genuinely, crucially important for allowing life to successfully emerge and persist on our planet at all. Let me try to properly unpack why this idea is genuinely significant, rather than simply stating it and moving on. The interstellar medium, as we briefly mentioned earlier tonight, is not uniform throughout the galaxy. It varies considerably, denser in certain regions, more sparse and tenuous in others, alternating as our solar system, along with billions of other stars, continuously orbits the distant galactic center, periodically passing through different regions of this varying interstellar material across the course of hundreds of millions of years. If our solar system had happened to be travelling, at this particular moment in its long galactic orbit, through a considerably denser region of interstellar material, the resulting pressure against our heliosphere's protective bubble would likely be correspondingly stronger, potentially compressing our protective shield considerably closer to the Sun, potentially reducing its overall effectiveness at blocking incoming cosmic radiation, potentially exposing Earth and the other inner planets to meaningfully increased levels of cosmic radiation across long evolutionary timescales. Instead, our solar system currently happens to be travelling through a genuinely favourable, relatively low-density region of interstellar space, sometimes called the local bubble, a vast, sparse cavity within the wider interstellar medium, apparently carved out over millions of years by a series of ancient supernova explosions that occurred somewhere in our galactic neighbourhood long before our own solar system had even properly formed. This particular favourable location, combined with our own sun's own specific level of activity and the resulting strength of its solar wind, has produced a heliosphere genuinely capable of providing meaningful, significant protection against the harsher radiation environment of wider interstellar space. Protection that, quite possibly, played a genuinely important, foundational role in allowing life on Earth to successfully emerge and persist across the full, multi-billion-year span of our planet's biological history. Wherever you are, I hope you're comfortable. I want to sit with this particular idea for a while now, because I think it's genuinely one of the more quietly profound realizations available within tonight's entire conversation. Consider, properly, what this actually suggests. The specific conditions that have allowed Earth to remain habitable, that have allowed the delicate, patient chemistry of life to successfully take hold and then persist, uninterrupted, across billions of years of continuous biological evolution, are not simply a matter of Earth's own particular characteristics, its distance from the Sun, its atmospheric composition, its abundant liquid water. They also depend, in a genuinely significant way, on factors considerably larger than our planet itself, on our entire solar system's specific, particular position within the wider galaxy, on the specific density and character of the interstellar material our Sun's protective bubble happens to be pushing against, on the accumulated legacy of ancient supernova explosions that, millions of years before our solar system even existed, happened to carve out exactly the kind of low-density cosmic neighbourhood our heliosphere now benefits from. There is something genuinely humbling and genuinely beautiful in properly understanding the true scale of factors that had to align, not through any kind of purposeful design, but simply through the patient, in different unfolding of cosmic and stellar history. In order to create and maintain the specific, delicate conditions that eventually allowed something like you resting here right now, listening to this, to exist at all. Let me bring us back, now, more directly to the specific instruments actually making these discoveries, because I think the human story behind this ongoing research deserves genuine, careful attention as well. Voyager 1 and Voyager 2 were launched in 1977, designed, originally, for a primary mission expected to last approximately 5 years. Enough time to complete flybys of Jupiter and Saturn, gathering data and images that, at the time, represented genuinely revolutionary advances in our understanding of the outer solar system. Nearly 50 years later, both spacecraft remain, remarkably, still operational. Still transmitting data back to Earth. Still, patiently, faithfully continuing a mission that has now stretched, unbroken, across 10 times its originally planned duration. This is a genuinely extraordinary achievement of careful, patient engineering and of the continued, dedicated attention of the mission scientists and engineers, some of whom, like Edward Stone, have remained personally, directly involved with this single mission continuously across the entire span of nearly 5 decades. Both spacecraft are now genuinely approaching the practical limits of their operational lifespan. Their nuclear power sources, radioisotope thermoelectric generators, converting the heat produced by the slow, steady radioactive decay of plutonium into usable electrical power, continue to gradually, inevitably weaken with each passing year, forcing mission engineers to make increasingly difficult decisions about which specific scientific instruments to power down in order to preserve enough remaining electrical capacity to keep the spacecraft's most essential systems and their most scientifically valuable remaining instruments functioning for as long as possible. Scientists studying the ongoing stream of data from both spacecraft have noted that the next meaningful opportunity to gather additional direct, first-hand data about this same boundary region will likely come from New Horizons, the same spacecraft, discussed in our previous conversation together, that captured our first detailed close-up images of Pluto back in 2015. New Horizons is expected to reach its own heliopause crossing sometime around 2030, though its own power supply is not expected to remain functional much beyond the following decade. Beyond that, scientists have begun discussing the possibility of an entirely new mission, sometimes referred to, in early planning stages, as an interstellar probe, specifically designed, from the very beginning, to study this boundary region in considerably greater detail than either of the aging Voyager spacecraft, launched decades before this research area had even been properly identified as scientifically significant, were ever originally equipped to provide. I want to spend some time now, gently, connecting all of this back to something more immediate, something closer to home, before we begin the slow work of bringing tonight's conversation toward its close. We've spent this entire evening exploring a boundary that exists, right now, at this very moment, roughly 14 billion miles from where you're currently resting. A vast, invisible, genuinely dynamic membrane, actively, continuously protecting our entire solar system, including this small, quiet room, including you, specifically, personally, right now, from the harsher radiation environment of the wider interstellar space beyond. This protection has been happening, faithfully, continuously, for the entire span of Earth's biological history. Long before human beings existed, long before anything capable of understanding or appreciating this protection had ever emerged, and it will, in all likelihood, continue happening tonight, tomorrow, and for the entirety of the Sun's remaining stable lifetime, regardless of whether anyone happens to be aware of it. There is something genuinely worth sitting with, I think, in properly understanding that you exist, right now, safely, comfortably, within a vast, actively defended cosmic space. A protective bubble carved out by our own Sun's continuous, patient outward breath, pushing back, hour after hour, day after day, year after year, against the harsher radiation environment of the wider galaxy, entirely independent of anything you've ever done, entirely independent of your awareness of its existence, simply, faithfully, continuing to provide exactly the kind of protection that has allowed life on this planet to successfully persist across billions of years. Let me offer you something more now about what this particular kind of protection actually costs in the most literal physical sense, because I think it's worth understanding properly. The sun's solar wind, that constant, continuous stream of charged particles flowing outward in every direction, creating and maintaining our entire heliosphere's protective bubble, represents a genuine, ongoing loss of mass from the sun itself. Every single second, our sun loses approximately 1 million tons of its own material, carried outward on the solar wind, continuously, faithfully, replenishing and maintaining the vast protective bubble surrounding our entire solar system. 1 million tons every single second. And this has been happening continuously for the entire 4.6 billion year history of our solar system, and will continue happening at broadly similar rates for billions of years still to come, as our sun continues its own long, stable main sequence lifetime. There is something genuinely moving, I think, in properly understanding that our own continued safety, the specific, delicate conditions that have allowed life on Earth to successfully emerge and persist, depends, in part, on this vast, continuous, genuinely costly outward flow of solar material, faithfully maintained, second after second, across billions of years, without pause, without exception. Entirely independent of anything happening here on the small, quiet planet, this protection happens to be shielding. Wherever you are, I hope you're still comfortable. Let's widen our view a little now and talk about what all of this reveals, more broadly, about the specific relationship between our solar system and the wider galaxy we belong to. For most of human history, we understood the space beyond our solar system in almost entirely theoretical, entirely abstract terms. A vast, largely unknown darkness, filled with distant, twinkling points of light that we had, until remarkably recently, no direct means of properly, physically investigating. The Voyager missions, patient and faithful across nearly 5 decades of continuous operation, have fundamentally, permanently changed this. For the first time in the entire history of our species, we possess genuine, direct, first-hand measurements of the actual physical environment existing immediately beyond our own solar system's protective boundary. Measurements that have revealed, repeatedly, patiently, across more than a decade of continued observation, that this environment is considerably more dynamic, more genuinely complex, more actively influenced by our own sun's ongoing activity than earlier, simpler theoretical models had properly anticipated. This is not, properly understood, a discouraging or frightening realization. It is, instead, I think, a genuinely remarkable testament to exactly how much there still remains to be properly discovered and understood, even within our own relatively nearby cosmic neighborhood. How even a boundary as fundamental, as significant as our own solar system's edge continues, even now, nearly 50 years after the spacecraft that finally crossed it were first launched, to reveal genuine, meaningful surprises to the careful, patient scientists studying the data it continues, faithfully, to send back. I want to offer you one final, broader reflection now, before we begin properly closing tonight's conversation, because I think it connects everything we've discussed this evening into something genuinely worth carrying with you towards sleep. The space beyond our solar system, properly, honestly understood, is not simply worse than we previously thought, in any simple, straightforwardly alarming sense. It is, more accurately, considerably more complex, more genuinely dynamic, more actively, continuously contested than our earlier, simpler theoretical models had suggested. A genuine, ongoing battle, playing out continuously, right now, at this very moment, roughly 14 billion miles from where you're resting, between our own sun's protective outward breath and the harsher, more energetic radiation, environment of the wider interstellar medium beyond. And within that ongoing, continuously contested boundary, our own small, quiet planet has managed to remain safely, comfortably protected for the entire multi-billion-year span of its biological history. Protected not through any kind of guaranteed cosmic safety, but through the specific, genuinely fortunate alignment of countless particular factors. Our solar system's fortunate position within a relatively sparse region of the wider galaxy, our own sun's particular level of ongoing activity, the accumulated legacy of ancient, long-past supernova explosions that happened millions of years ago, to carve out exactly the kind of protective cosmic neighborhood our heliosphere now benefits from. None of this was guaranteed. None of this was inevitable. And properly, honestly understanding the genuine complexity, the genuine dynamism, the genuine ongoing tension involved in maintaining this particular delicate cosmic safety, makes the actual fact of your continued, comfortable existence here, tonight, in this quiet room, feel, I think, considerably more remarkable than a simpler, more static understanding of space ever properly could. Let's come down now, slowly, gently, toward the end of tonight's long conversation. Here is what is true, as carefully and as honestly as I can leave it with you. Our entire solar system sits within a vast, invisible, continuously active protective bubble called the heliosphere, carved out and maintained by the constant outward pressure of our own sun's solar wind. This bubble genuinely, significantly protects Earth and the other inner planets from the harsher radiation environment of interstellar space, blocking approximately 70% of incoming cosmic radiation. Direct measurements from the Voyager spacecraft, which crossed this boundary in 2012 and 2018 respectively, have revealed that this protective boundary is considerably more complex, more dynamically active, and in certain specific ways more surprising than earlier theoretical models had predicted, containing unexpectedly hot, energetic plasma regions, imperfect, porous areas of reduced radiation shielding, and a genuinely surprising, ongoing connection to our own sun's activity that extends considerably further into interstellar space than previously understood. None of these findings represent any kind of immediate threat to life on Earth. What they represent, instead, is a genuinely more complete, more honest, more properly detailed understanding of exactly how our solar system's protective boundary actually functions. An understanding built, patiently, faithfully, across more than a decade of continued observation, by two extraordinarily long-lived spacecraft launched nearly 5 decades ago, that continue, even now, to reveal genuine, scientific surprises about the specific, delicate cosmic conditions that have allowed life on this planet to successfully persist. I want to leave you with one final image before we close, because I think it captures, better than any additional detail could, the particular feeling I hope you carry with you into sleep tonight. Picture, if you can, 2 small, aging spacecraft launched during the same decade that first put digital wristwatches into ordinary people's hands, now traveling, faithfully, patiently, silently, through the genuine darkness of interstellar space, well beyond the protective boundary of our own solar system, sending back, across the vast distances involved, faint but genuinely precious streams of data about a cosmic environment no human instrument had ever directly measured before. And here, safely, comfortably, within the protective bubble, those same measurements have helped us properly understand you rest, shielded, right now, at this very moment, by billions of years of accumulated cosmic fortune, a favorable position within the wider galaxy, a sun whose continuous, patient outward breath has faithfully maintained a protective boundary across the entire span of Earth's biological history, and countless other particular, specific factors, none of them guaranteed, none of them inevitable, that happened patiently, faithfully, to align in exactly the way required to allow something like you to exist at all. Thank you for spending tonight here. Thank you for letting something this complex, this genuinely surprising, become something worth understanding properly, honestly, carefully at this hour. Sleep well, and somewhere, roughly 14 billion miles from where you're resting, 2 small, faithful spacecraft continue their long, patient journey outward, still sending back, across the growing distance, whatever new secrets the space beyond our solar system continues, quietly, to reveal. Good night.